Okay, so for each of the following matrices A within M n by n, the real numbers, test A for diagonalizability, and if A is diagonalizable, find an invertible matrix Q and a diagonal matrix D such that Q inverse A Q equals D. And the problem we're doing is 2B. So we have our matrix A, and the first part is we're going to test whether or not A is diagonalizable. And we do that by checking whether or not the characteristic polynomial splits and if the multiplicity of each eigenvalue is equal to the dimension of the vector space, which in this case is R2, minus the rank of our matrix minus the eigenvalue times the identity. Now the way we test for the splitting of the characteristic polynomial is we look at the determinant of A minus some number times the identity matrix, which is the determinant of 1, 3, 3, 1 minus T 0, 0, T. And this equals the determinant of 1 minus T, 3, 3, 1 minus T. Alright, we can expand that out. This equals 1 minus T squared minus 9. And we can see we can write that in a form of a splitting polynomial. So this comes out to T squared minus 2T minus 8. And this could be factored to T minus 4, T plus 2, which indeed does split over the real numbers. And if you don't know, a splitting polynomial can be factored into a product of linear factors. So something that looks similar to this. So for example, this splits, but T squared plus 1 does not split. Let's change colors here. Okay, so this produces, we look at the zeros of this polynomial, and then we have eigenvalues of lambda 1 equals 4 and lambda 2 equals negative 2. And each of these have multiplicity 1 because these are all only to the first power. Alright, so our characteristic polynomial splits. Let's test this second requirement about the multiplicity of our eigenvalues. We'll do lambda 1 first. So remember, lambda 1 has multiplicity 1. So let's look at the rank of the matrix of A minus our lambda 1I. So rank, I'll write this up, clean this up a little bit. So rank of A minus 4I equals rank of negative 3, 3, 3, negative 3, which clearly has rank 1 because all you'd have to do is negative 1, or I'm sorry, not even negative 1. You just add this first row to the second row, and you could zero out the second row here, and you would be left with one linearly independent column. So that equals 1. And n in this case, or in the case of this whole problem, is 2 because dimension R2 equals 2. So we have now n minus our rank a minus 4i equals 2 minus 1 equal to 1. And that equals our multiplicity of lambda 1. Okay? So that checks out, but we still have to check our other lambda value because we did have 2. Oh, didn't want to delete that. Alright, so now on to lambda 2. So lambda 2 does have multiplicity of 1. So now let's look at the rank of the matrix, a corresponding matrix to lambda 2. Rank a minus a negative 2, which is plus 2 I, equals rank 3, 3, 3, 3 equals, again, it's easy to see, will be equal to 1. Because we could just zero out either a row or a column by just taking the negative of the other row or column. So just like the other one, since the rank is 1 here, our dimension, which is 2, minus the rank there, 1, equals 1, which is the multiplicity of our second eigenvalue. In the next video, I'll show you how to find a basis for the eigenspace corresponding to each eigenvalue, lambda 1 and lambda 2.